curvature tensor by a contraction, which throws away information. And in particular, in the first lecture, we assumed that the curvature was bounded, but the Einstein equation, if we normalize the Ricci curvature in dimension 4 and above, this doesn't guarantee that the curvature is bounded. And so the main concern, in a way, is what happens when the curvature gets big, how to describe what happens in that situation. So it definitely can happen. So the contraction, because of the symmetries of the curvature tensor, produces a symmetric bilinear form. And therefore, it makes sense to look at metrics for which this symmetric bilinear form is just proportional to the metric. And that's the Einstein equation. So these manifolds arise in different ways, of course, and this is not the Lorentzian case where you have general relativity, but nonetheless in algebraic geometry and so on, according to the Calabi conjecture, particular Yau solution of it, these manifolds arise naturally. And viewed in an appropriate local coordinate system, the Einstein equation is some kind of elliptic equation. But of course, first of all, not a linear one, and second of all, the equation is, there's no background metric. So there's no, the space and the equation are coupled together. And both of these mean in particular, so an elliptic equation, any sensible solution doesn't have any singularities, but in this case, of course, you can have singularities, and the fact that you don't have a fixed background metric in some ways makes the situation harder to study. In other ways, because it arises naturally in geometry, there are certain theorems in geometry which work to your advantage, and that kind of saves you. So there was an example which was particularly illuminating, a metric on the tangent bundle to the 2-sphere, which at infinity just becomes rapidly asymptotic to R4 divided by Z2. Both of those, the infinity of this vector bundle looks like R plus cross RP3, and topologically it's the same as the infinity of R4 divided by the antipodal map. Z goes to minus Z. So it makes sense to say there's a metric on this that's asymptotic to the flat metric. And indeed, we can let's just believe that there is such a metric. The Ricci curvature is identically 0. It has all the symmetries you expect it to have, moving points on S3 around, rotation in a fiber. And it also happens to satisfy that the integral of the L2 norm of the curvature is finite. So
is it something algebraic, monoid?
Is the metric algebraic?
Yeah, it is. You have a space, which you consider as a flat space, essentially. So the question is whether you can write a metric or you can judge any coefficients since you have your rod are forced, which chosen coordinates. If you are writing this
certainly, yeah, you can write a simple formula for it. That's for sure. It's not illuminating particularly for our purposes. But you can write it, yeah. If you have one metric that's Ricci flat, you can scale the metric and get another one. In particular, you can multiply it by a small number, and this makes the 0 section, which is actually a totally geodesic 2-sphere, extremely small because it's rapidly asymptotic to infinity. It brings infinity in and becomes a flat cone in the limit. It just becomes. So this shows that, of course, in the scaling, since it's not flat, if I scale it in, the curvature blows up. So this certainly shows Ricci flat in dimension 4. Doesn't put any bound on the curvature. Very small balls have non-trivial topology. And in the limit, we just get this flat cone, and this turns out to be quite typical. So I haven't strictly defined the limit, but everyone can kind of see what it is. It just looks to the naked eye the limit of the scaling process is R4 divided by the antipodal map. So singularities can form in the limit. So if we want to describe, which is going to be the goal in this lecture, what sorts of singularities can form, and in particular in higher dimensions, we need to have some criterion for recognizing whether a ball was singular or standard. And so here was the basic epsilon regularity theorem from last time. So I won't review anything that was special to dimension 4 because today we want to talk about the higher dimensional case. So this theorem, the formula is what may be slightly complicated. We've normalized the Ricci curvature to be that of bounded in absolute value of the Einstein constant of the Ricci curvature by that of hyperbolic space. And what this says is if this scale invariant power of the curvature, this quantity is invariant under scaling the metric for this particular power, n over 2, is sufficiently small relative to this quantity, which we call the collapsing, the volume of the ball divided by this comparison ball, which would be the biggest it could be. So if this, the amount of curvature measured in this sense, is small enough, some constant depending only on the dimension relative to the collapsing, then on a ball of, let's say, half the size, really on any concentric ball with a different constant, you get a definite bound for the section curvature. So once the integral, the scale invariant integral is small enough, then the curvature is bound. But you don't automatically have this hypothesis satisfied for a given ball. Nonetheless, if you have a bound on this ln over 2 norm, an explicit bound, somehow maybe this one I'm going to put over here and leave it here for a while. So nonetheless, if you have an explicit bound on the integral, the same normalization, then there are only, I don't know how the focus is here. Could improve it too much. Is that better? Okay. So using this criterion, then there could be only, so to say, so many balls, let's say, of a fixed size to start out with, where that criterion was violated, because each time it's violated, you need, on that ball, the integral has a certain definite size. So there couldn't be too many disjoint balls, certainly, for example, where it was violated by a standard covering lemma. There can't be too many balls, period. So it leads to this particular conclusion, that if you happen to, for some reason, either because you assumed it or for some other reason, have a definite bound on this, so then there could be some points at which the curvature could be uncontrollably big, but away from those points it's bounded, and as you move into those points, it's some universal constant, independent of the metric times distance to the -2. So of course, on a given manifold, it remains finite at those points, but this is an estimate that's independent of the manifold. Okay, so let's just leave that up there, maybe, and keep the other example of the scale down at Ricci enhancement in mind. Okay. So we had some special results about the collapse case in dimension 4. Today, we want to go beyond that, and at the moment, there isn't too much you can say about the collapse case that seems realistic. So there is some structure theory for collapsed spaces just with a lower bound on the Ricci curvature in higher dimensions, but adding Einstein and integral bounds doesn't tell you too much more at the moment. So therefore, rather than go into the technicalities of the collapse case, which seems still pretty far from reality, I want to talk about the non-collapse case in higher dimensions. So that means we assume that the volume of every metric ball of size 1 has a definite lower bound. Okay. So we want to discuss some conjectures and results. They should look eventually like some joint with one or both of them. So the title of the lectures is about small-scale structure, but I want to today weaken the problem slightly. You capture a lot about small-scale structure, but not everything. So that is, instead of just asking for the small-scale structure, it's convenient in the course of studying that, to imagine that you go to the limit of sequences of bad examples where you allow singularities to form. Now, of course, you have to go to the limit in some suitable weak sense. The topology was strong enough, the sense of convergence was strong enough that singularities couldn't form. But you want some weak sense that kind of captures everything possible, and you try to understand what the singularities look like. So, I mean, for example, with the scale down to Gucci-Hansen, you would say that in the limit we get R4 modulo the antipodal map, which has a very simple kind of singularity. It doesn't tell the whole story because this little S2 popped off at the end, but certainly knowing what the limits look like, you could then imagine trying to go backwards. And if you didn't imagine that, it would tell you a lot about what happened before you went to the limit, if not everything. Of course, things can indeed pop off. So I want to concentrate. What's that?
If you start with point in the limit.
If you start with what?
A point in the limit.
Yeah.
Would you construct some kind of universal family of deformations? Because if you have usual singular variety, algebraic geometry, the natural thing to do is consider all possible deformations. In many cases, on the open set, majority of the
I don't know exactly, but just kind of slightly avoid your question. I don't assume that the sequence has constant topology or anything. Okay. So you might even have different sequences, totally different manifolds converging to the same limit. Okay. So we imagine that what are the worst examples, and then we pass to the limit and we get some singularities. We try to describe what these singularities could possibly look like. So the two problems, of course, of the small-scale structure and the singularities have to be studied kind of in tandem, because if you didn't have some estimates or information that was independent of the particular manifold, dependent just on the scale, how could you possibly tell something about the limit, right? I mean, you can only study the limit, because it's a limit of manifolds by studying the manifolds. But as in other contexts, it's very convenient to move back and forth between the two and kind of have a bootstrapping like argument. So intuitively, when I talk about limits, although it's certainly more than scaling, I'm thinking of a sense of closeness where two things intuitively, they look close if it's hard to distinguish them. You can't see that they're different. Of course, if you have a powerful microscope and you examine them, they might look entirely different, right? But if you don't have access to such an instrument, to you they look the same. Then I consider them very close. So this is quite a good intuition. And so here's a technical definition. So first, let's imagine that the objects that we're talking about are just compact metric spaces. So this is really Gromov's abstraction of the classical notion of Hausdorff distance between subsets of a fixed metric space. We have two subsets, but they're not subsets a priori, the same thing. So this is one way of abstracting. So we say that a sequence converges if we can find for any epsilon here, these are points in the limit, these are points in the approximating thing that converges to the limit. They have a definite number of members, and pairwise the distances are close. So this captures the idea that they look the same to the naked eye. Now, using this Bishop-Gromov inequality or relative volume comparison, or one might just say the doubling property of the Riemannian measure, subsequence would have a limit, which is something, but a priori, who knows what it is. So this kind of pre-compactness property holds when you have a bunch of metric spaces that are compact, and they're uniformly totally bounded. You can find an epsilon dense set with n of epsilon members, which depends only on epsilon, but it's independent of the member of your family. So this is a totally soft theorem and an easy theorem, but it's a great organizing principle in the subject. It's a big advance. But this is not hard in and of itself, but it's very essential and used all the time. I mean, it's a very fundamental tool. It's just, it gets you going, you use it all the time, but it's not difficult in and of itself. Now, there's also a technical notion, a slight extension of it, which is important to us because we use it to define this basic notion of tangent cone, which is how you study the infinitesimal behavior of these limit spaces, describing the tangent cone instead of the tangent space. So the spaces don't have a bound on the diameter. We could generalize the notion of a convergent sequence by saying converges to a limit space if on every ball the sequence of balls converge. So it's like, you know, uniform convergence on compact substance in that spirit. So you have to fix a base point in order to reduce it to compact case. The other definition would make sense, even if the spaces had unbounded diameter, if you didn't stipulate the sets were finite, but it's not the right notion. This is the right notion, and by a diagonal argument, you still have convergent subsequences in this sense. And this is, well, I chose to say it now while we're talking about going off Hausdorff distance, but you really need this. It's not just for generalization that you make this definition. Okay. So, as I mentioned, we want to consider in this talk only non-collapsing sequences because we can't say too much. We can say something, but not using the Einstein condition in an interesting way. So we want to restrict attention to limits where volumes of balls, unit balls, have a definite lower bound. So that's all we're going to look at for the remainder of the talk. This turns out to be equivalent to saying that the limit space has Hausdorff dimension n. And in fact, if it collapses, it really has Hausdorff dimension at most n-1, which sounds plausible, although it's not obvious. N-epsilon or something. But actually, either it has dimension n, which is equivalent to this non-collapsing condition, or it drops by at least 1. So that turns out to be true. Okay. So now, from the same epsilon regularity theorem that led to this, it's quite clear that the corresponding result, if we allow ourselves to pass the limits, is that it certainly appears there should be at most, if we bound this integral, take us a convergent subsequence which doesn't collapse, but there should be at most a definite number of singular points. And this is true. And they also turn out to be actually orbifold singular points for which you have to work somewhat harder. We'll see from a more general standpoint why we expect this singularities to be infinitesimally like cones from the fact that you would certainly expect that this would mean that the regular part, away from the singular points, the integral should still be finite. In fact, it should be smaller because something concentrated at the singular points. Away from that, where things are smooth, you should have convergence, so the integral should still be bounded. So near any singular point, if you remove the point itself and look at a small disk, the integral will be very small, or a small enough ball, I suppose it's convergent. So if you rescale now to unit size, the integral looks really like it's small over a ball of size 1 centered at that point. And that's an ingredient on the way to this orbifold structure. So it's this tangent cone, if you believe it should be a cone, which we'll come back to momentarily, should be a flat cone, just because the integral is finite. And eventually you show something like the singularity is removable, Einstein manifold. And those are Einstein manifolds with so-called special holonomy, which simply means that the holonomy group is smaller than the biggest it could be, which is everything. So these manifolds, by the way, the possibilities for the holonomy group and what it could be are all classified. This is work of Berger and Simons and some other people. The most interesting one, I mean, most familiar are Kähler manifolds, and there are Kähler manifolds that are Ricci flat. We have an example of K3 surfaces. An example of that, these are interesting in string theory. There are special Kähler manifolds called hyper-Kähler manifolds where you have 3 complex structures. There's some generalization of that called quaternion Kähler. There's holonomic group G2 and spin 7. Those have dimensions 7 and 8 respectively. So if this is not familiar, you can safely ignore it. Just think of the Kähler case. That's too much. Just ignore it altogether. But the theory is more complete. If we make this extra assumption, many of the most interesting examples are exactly of this type. So I mentioned this, but if it's too much of a distraction, ignore it. Most of what I say is either true or conjecturally true, or with a suitable modification true, even without this assumption. But so I don't have to keep mentioning technicalities. Sometimes this hypothesis will appear. Okay, so as I said, the most familiar example is Kähler manifolds. These are manifolds with an almost complex structure that's an isometry. So J is an isometry, J squared is -1, and J is parallel, which is equivalent to saying that this, which is a 2-form of maximal rank, is closed. Okay, and the Iguchi-Hansen manifolds that I described are of this type. The metric is actually Ricci flat, so they're special Kähler. It's called Calabi-Yau. In fact, they have even 3 independent anti-commuting, almost complex structures with this property. Just the same. It doesn't end, but just to have one example that we mentioned. Okay, and as I already said. So that I don't have to go into technicalities in the statement, this word will sometimes appear. You can think Kähler, or you can just ignore it if it's not familiar. Okay, so now, what should we expect if we think of generalizing what we did last time to higher dimensions? What might we expect? What kind of singularities could we expect? Well, although in this theorem and in the transparency I said earlier, we had a strong hypothesis, namely a high power of the curvature, the scale invariant n/2 power that was bounded, and we had only isolated points. This certainly will not be kind of the general situation, because I could just take a product with a 4-dimensional thing, and I'll get codimension for singularities. The singularities cross this thing I'm taking the product with. Now, of course, the Ln/2 norm won't be bounded, but why should I suppose that that's the case? It's an interesting but not typical case. It's not the typical case. It's a highly special case. So it's not generic. So what I might expect then is that, and what is expected, is that the typical case might be that the singular sets that form have Hausdorff codimension 4. That's what this suggests. Just by taking products with the 4-dimensional. So that's a reasonable expectation. Shouldn't be possible to do any better than that and still include these simple examples. Okay. So now here is the first theorem, which says that if I have a sequence of manifolds with special holonomy, non-collapsing, even if I don't say anything about the integral of the L2 norm, the singularities are going to be codimension 4. So that's a definite statement. Singularities of the Einstein manifolds will always be a closed subset because of an epsilon regularity theorem I didn't quite mention yet. They will in fact be closed, and they will be codimension 4 if it's a sequence of manifolds of special Holonomic. I don't say anything more about the structure of the singular set, but it will have Hausdorff codimension 4 with generality. This is conjectured, so as we go on, I'll give more of an indication about how one might, what some of the things that are used in proving this. But anyway, the singularities are always of codimension 4. It's special and conjecturally in general, but embarrassingly, it's not known yet for arbitrary Einstein manifolds. But it is at least known through what are in part case-by-case arguments. I mean, they always have the same general structure, but the details are different at the moment from case to case. You can prove it for special holonomic. Conjecturally, it's true for non-collapse limits of Einstein manifolds in general. So there's a fact, and as we go on, we'll be able to get a little bit more idea of what's used in proving it. Now, here's another thing that's good about special holonomic. We saw in the four-dimensional case that the L2 norm of the curvature was just point-wise a multiple of the Gauss-Bonnet form, suitably interpreted. L2 times the local volume form, oriented volume form, is proportional to the Gauss-Bonnet form. So that the assumption on the L2 norm of curvature was particularly natural in dimension 4 because it came to you for free if you fix the topology. Now, for special holonomic, there's a corresponding fact in higher dimensions. And again, it relates to the L2 norm of the curvature, not to the Ln over 2 norm of the curvature. The Ln over 2 norm was very convenient. For example, with scale invariant, this is a much weaker assumption. However, sometimes it comes to you for topological reasons without explicitly assuming it. So what I'm saying is for special holonomic, there's some characteristic number. So by characteristic number, I mean I allow it, let's say, here's in the, say, Ricci-flat Taylor case, here's the formula. So it involves both the second Chern class, which is, and the Taylor form. But it depends only on the cohomology classes of those two. So in that sense, it's topological. It doesn't depend on the metric, only on the cohomology class of the Taylor form, and on this thing that's independent. Depends only on the information class of the complex structure. So this indicates that the L2 norm continues to play a distinguished role in higher dimensions. You would like to prove things. If you have to, I mean, it's kind of a weak thing to fix the topology. The previous result didn't require that. But if you wanted to bound something, you would like it to be the L2 norm because that comes to you without just assuming it. You get it in interesting examples for this reason. But it's no longer scale invariant. It's a much weaker assumption in higher dimensions, so you need different kinds of theorems in order to be able to get something out of it. Okay. So here is a definite conjecture. It's not the strongest thing you could say, but it's actually pretty strong. And again, something like this, something like it is presumably true even without the special holonomic assumption. But I won't go into that. It's at worst pretty true without that, maybe. But so the assumption is so that a reasonable generalization case, in effect, crossed with something tricky, crossed with something smooth. So that's the conjecture. Not that the metric is literally a product, but it's an orbifold of this type. That's the conjecture. And here is the progress in words. And then the rest of the talk, I want to say some description of how you get to this. So the first statement is that it's true kind of at the infinitesimal level. Namely, there is a four-dimensional piece of the singular set where if you blow it up, you inspect it under the microscope, you actually, so you take the limit under rescaling in this Gromov-Hausdorff sense. So you get a tangent cone. You'll always find at least one tangent cone that looks like a flat orbital. That's the first thing I want. And at almost all points, that's the only tangent cone. So when we talk about tangent cones in a minute, we'll see they're not automatically unique. So first of all, the conjecture is true at the infinitesimal level. That's one statement. And another, just like spelling error here, another point about the more fixed scale structure of the singular set. You can't say it's a manifold, which you might think. Something like a stratification. We don't know this yet. But we know it has locally finite N-4 dimensional Hausdorff measure, so that's good. And in fact, in the measure theoretic sense, it's like a Lipschitz measure. So that's what we happen to know. That's called being rectified. And it means you can throw away a set of N-4 dimensional measure 0. It's a countable union of things, pieces that are pi Lipschitz to Euclidean space. So this is a kind of technical condition. It's like being a manifold in the Lipschitz sense almost everywhere. Something like that, except you have measurable sets instead of open sets. Otherwise, it's like being a Lipschitz manifold. This, we hope, this is what we can do at the moment. We hope it's far from the truth because we hope the orbifold conjecture is true. But this could be, in other contexts, a useful step along the way. In other contexts, something like rectifiability has been a useful step in proving stronger results. And even in classical cases like harmonic maps and minimal surfaces, where the truth might also be something like this, the best results about the singular set so far, they typically say they're rectifiable, and they're not easy to prove there either. So this is what we can do at the moment. And so this obviously makes it look at least plausible, but the part that remains is still probably very hard. Okay. So, as in the previous situation, we always, if we're going to say something that the singular set is small, we have to have some way of recognizing that the regular set is big, which means we have to have some way of recognizing when the ball is good, standard. Now, the previous lecture, we talked about this epsilon regularity theorem, which required the non-collapsing, and this entered as an ingredient for controlling the Riemannian constant. And that's all we had to know. So we had to know the ball is not too collapsing, and this is small relative to the collapsing. We didn't have to know anything about the shape of the ball. Right? There's nothing else that's mentioned here. Nothing about the shape of the ball except this. But we're bounding a high power of the curvature. Now, we want to have epsilon regularity theorems. We would need, clearly, bounding only the L2 norm instead of the Ln over 2 norm, which is a much weaker assumption. So now I want to describe such theorems or say something about them which exist, but we'll have to assume more about the shape of the ball in order for them to be true.
True or true?
What?
Be true or be proven?
No, be true. No, be definitely true. I mean, you just think of the case with the Iguchi-Hansen manifolds. Well, just kind of to give some indication. something about its shape, that it's close to one of these orbifolds, like cones, where it has a certain big Euclidean factor, right? So when this is big, it's more close to being regular, of course. So therefore, there should be a correspondence between this being big and the power of the curvature that we have to control. The bigger we assume the factor is, the smaller the power of the curvature should be. So, in fact, in this special holonomy case, as I previously kind of indicated from the first result that didn't involve assuming anything about the integral, if k is less than 3, if it's close to a cone with Euclidean factor n minus 3, then you don't have to assume anything about the integral. Just normalize the Ricci curvature and that's it. And as is indicated by this one, for the case n equals 4, if k is 4, so it's Rn minus 4 across a 4-dimensional flat cone, then it's enough to assume that the L2 norm is small, right? So that's kind of a direct generalization of this one to dimension n, but where we start with n equals 4 over there and then cross it with some Euclidean space. So these are the two main ones that are of interest today, but there are corresponding ones for any k. But I want to stick to a bound on the L2 norm at worst because that's the most relevant, because it comes for topological reasons. So it's sort of the generic case. So there's a correspondence for any k, actually. All right, now here, the weeks, I've been saying I have to draw this picture, and I see I forgot to draw it. So here's a different way of proving an epsilon regularity. So I just give a different kind of argument, and that's, but this kind of argument, but souped up, combined with a kind of slicing argument, is the way that these theorems are proved. So the technical part, because you have this Euclidean factor, is substantial, but ultimately you reduce it to the following kind of argument. So suppose that someone showed you a manifold that looked like this. So to you it looks like a cone. And this is kind of blown up, but let's imagine it's really so small that you can't see what's in here. Okay? So it looks like a flat cone as far as you can see, but you can't really see what it looks like near the tip. And now suppose, so you can see that the part you can see, the curvature looks like 0. This is a 2-dimensional surface, looks like just like a cone, paper cup. But here, this part you can't see. Now suppose someone says that this is really a smooth surface, and I swear to you that the integral of the curvature, the L1 norm, over this part that you can't see, is extremely small. Imagine he says it's 0. You know, really much smaller than it's supposed to be. So the question is, since you can't see it, is he telling the truth or not? And the answer is, of course, no, he's not telling the truth. And why? Because it would contradict the Gauss-Bonnet formula, right? So the boundary term from the picture is away from being an integer. It's between 0 and 1, the boundary term in 2-dimensional Gauss-Bonnet form. The interior part that you can see is manifestly small. The part you can't see, he tells you it's small. So if that were the case, then the interior plus the boundary would not add up to an integer, as the Gauss-Bonnet formula. So no matter what the topology was in here, the Gauss-Bonnet formula can't give you an integer. So it couldn't be telling. So now in our case, we have these things that have slices. So imagine k equals 2 in the previous one. We want to rule out tangent cones. K equals 2 under the appropriate integral bound. So we know that it's close to a picture like this, just crossed with the Euclidean space. So kind of, the idea is then you take your manifold, which is supposed to be close to that, and you want to slice it into something like 2-dimensional slices by some clever method, so that you'll be able to know that the typical smooth slice, a generic one, over a generic coordinate of Rn minus 2, it's close to a cone, most slices really look like this. It would be enough to have one look like this, but if you prove it at all, you would prove most look like this, meaning everything is exactly like this, then you would have a contradiction. So the idea is by some kind of, so if you think you give yourself that hypothesis, then by some sort of slicing argument, you try to reduce it to exactly this or the corresponding thing in higher dimensions. Turns out to be a little harder to do exactly this in higher dimensions, but in principle it's exactly like this. Technically it's a little different. But you want to show most slices look like this. That's how the epsilon regularity theorem would be proved. It's exactly, in spirit, nothing more than this, plus the technical part of how you slice it, which is non-trivial. How you prove that you really get this way. Then the other part is how would you verify the hypothesis that where, you know, on limit spaces would you find that you had cones that looked like this? How would you know that it looked like this? How would you know you have a lot of cones that look like this? So that's the other part of the discussion. So let's now assume that we understand the spirit of this argument, that if I can show it's close to Rn minus k across such a flat cone, I'll be able to, with small integral norm, appropriate integral norm of the curvature, I can slice it and reduce it to this picture where you contradict Gaussian. So the rest of the talk, I want to talk about how you produce flat cones in this situation. Euclidean space-times orbit. How do you get these cones into the picture so that you could verify, so that the hypothesis of the theorem would be satisfied. So a lot of the theory, as I mentioned last time, showing that tangent cones are just cones, not flat cones, but anyway, cones, you can do with the non-collapsing assumption in just a lower bound on the Ricci tensor. It doesn't have anything to do with Einstein. So there really is a fairly detailed theory of collapsed limit spaces just with a lower bound on the Ricci tensor. And then to that, well, in fact, there is a theory that doesn't even involve the collapsing, but that gives something that's okay. But let's think we add the collapsing. That's what we're interested in. The non-collapsing. That's what we're interested in here. And then we add the upper bound as well. That just is not such a big deal in the beginning. It just makes the regular part kind of more regular. Eventually we add these other assumptions. But a lot of it, the part about producing the cones, actually, you need something much bigger.
It's not hard to use a special holonomy.
Well, the special holonomy is kind of because I cheated a little bit by saying you can literally always reduce it to a slice as a nice cone. You can't really reduce it to Gauss-Bonnet all the time. I mean, conjecturally, maybe you could, but when the codimension is bigger, it's hard to control the second fundamental form well enough. So you actually have to, instead of using like the Gauss-Bonnet form on a slice, you have to use the second Chern form on the total space. And that already works in the complex case, otherwise there is no second Chern form. By doing something like that, you avoid having to estimate the second fundamental form, which is somewhat short of what you can control. You can't control it well enough when the codimension is big. But in spirit it's the same, but in practice you can't always reduce it to Gauss-Bonnet. You have to use some other characteristic. So, all right. So we want to study tangent cones, right? Because we want to eventually say that these cones that occur in the epsilon regularity theorem are tangent. tends to 0. So the thing to keep in mind is tangent cones have non-negative reaching curvature in a generalized sense. I haven't said exactly what tangent cones are yet, so let's say kind of indicated. So it's just exactly this. I take a point, I rescale. This is the distance function. Rho is the distance function. So I just blow it up, and it's easy to see that I stay within the category. So by Gromov's compactness theorem, it's a limit of limits. It can always take a limit. So any blown up limit, I'll call a tangent cone. They exist. I'm not saying it's unique. I'm not saying it's a cone just because I call it a cone. I'm just saying you can take these limits. What they look like, that says what the infinitesimal structure of your space is. Now, if you want to know what they look like. So, if it would be a flat Euclidean space, that would mean at least at the infinitesimal level, you would be at a regular space. For Einstein manifolds, it really would be a smooth. So you want to know, so that's a tangent cone, and morally, because they're gotten by blowing up, these things have non-negative curvatures. Now, what do we make of that? What's good about having non-negative curvatures? So the point is that so we should also know, because we blew it up, it would be non-compact, right? So it would look non-compact, and it would look like it has non-negative reaching curvature in some generalized sense. Now, the point is that for manifolds with manifolds with non-negative reaching curvature, there are theorems about it. They're rather rigidly constrained because the non-negative reaching curvature tries to make it close up. And if it's non-compact in a strong enough sense, the two things can only coexist under special circumstances. So from more than 30 years ago, this started for non-negative sectional curvature with Tapanago, and then Ramal and I waited for smooth manifolds with non-negative reaching curvature. There are rigidity theorems that say their structure is, in some sense, tightly constructed. And the basic tool for studying the limit spaces is to show that those theorems extend to the limit spaces. It took a long time. It's technically quite hard, actually. The Gromov-Hausdorff sense is exactly the correct measure, remarkably, of how they extend. But, so that's the idea. The tangent cones, when you pass to a tangent cone, you gain something because, in effect, you can pass from reaching bounded below to reaching non-negative in a generalized sense. So you can hope to say something about it. All right. So here's what I was just alluding to. Here's a theorem which was initially proved just for smooth manifolds with non-negative reaching curvature. First sectional curvature by Tapanago, reaching curvature by Ramal and myself. And then more after, almost 30 years later, for these limit spaces, which have. So if the space contains a line, so that says it's non-compact in a sufficiently strong sense. That line is of doubly infinite geodesic, each finite segment of which is minimal. So not all non-compact spaces contain this thing. But so to contain it, it has to be non-compact in a strong sense. This is what you're supposed to do. If that's the case, and the reaching curvature is non-negative, which tends to oppose non-compactness, then this line can only occur as an isometric factor. So this, since tangent cones have non-negative reaching curvature, this constrains the structure of tangent cones. Whether or not they're collapsed by it, this doesn't involve the non-collapsing. collapse case. There was one of them, which didn't use the non-collapsing. Here's another one which uses it. So far I haven't said that tangent cones in any sense are cones. That needs the non-collapsing assumption. And the for collapse limits, it wouldn't even be true. So in the non-collapse case, the relative volume comparison, if you look at the case, so it says a certain ratio is decreasing. If you look when the ratio is constant, you can see by the ordinary differential equation type techniques that it really looks like a warp product with the same warping function as in the space of constant curvature. What that amounts to in this case is that if you have a tangent cone, non-collapsed, then the volume behaves homogeneously, like a metric cone would behave. So from the point of view of volume, relative volume comparison, the first point is that it behaves like a metric cone. From the point of volume, but what's harder to prove, but it's true, and this is the other sort of basic tool, is that it's really like a metric cone, as would be the case for annuli in the smooth case. If from the standpoint of volume, they behave like a cone, then really from the standpoint of the metric, they behave like a cone. This is like the splitting theorem. And now the cone can have arbitrary cross-section. The cross-section is just something. You would expect, since your cone has non-negative Ricci curvature, the cross-section would have actually positive Ricci curvature, at least equal to that of the sphere. And therefore, by Meyer's theorem, if you know that, it should have diameter pi, which is true. This is consistent with at bigger than diameter pi, by the way, it couldn't satisfy the splitting theorem. Okay, so there are these two cones. There are these two rigidity theorems for tangent cones, or more generally for non-collapsed limit spaces. One for limit spaces with non-negative Ricci curvature in the generalized sense. One means non-collapsed, that's this one. Volume cones are metric cones. Both apply to tangent cones. So this is how you get cones into the picture, by proving these two rigidity theorems. And this is equivalent to proving the rigidity theorems in the smooth case, but allowing for errors in the hypothesis and the conclusion. You assume the hypothesis is almost satisfied, it's almost rigid, and then you have to show that the conclusion is almost satisfied. And it turns out, quite remarkably, that the appropriate almost in the conclusion is when measured in the Gromov-Hausdorff sense. Okay. So this much of the discussion just uses non-collapsed for the second part and Ricci bounded below. So now, using this, we have a limit space. We can divide it up into a regular set such that every infinitesimally regular, you can think every tangent cone is the Euclidean space, and the other points let's call singular. Now, something infinitesimally regular in the Einstein non-collapse case, it's really a smooth point. There's an epsilon regularity theorem that says that. Okay. Now, how can we then study the singular set? So this is a standard kind of thing in geometric analysis. We want to be able to distinguish levels of singularity. What are the most singular points, the next, and so on. And so we measure that by whether or not there exists a tangent cone which splits off the Euclidean factor of pi dimension. Okay. If there's no tangent cone at the point which splits off r k plus 1, we'll say it's an sk, which we think of as being like the k scale. If you imagine this singular space as a simplicial complex. Right? And along the k simplices, they split off the Euclidean factor of their dimension. And then the perpendicular dimension is the cone on the length. And the length could be whatever it is. So this kind of decomposition is a definition, but it's inspired by the picture of a simplicial complex. And similar things occur elsewhere in geometric analysis, and there are also similar conclusions bounded below. And this SK part has Hausdorff dimension at most k. So that's the first thing that's true. This is proved by a blow-up argument, where both of the two rigidity theorems I mentioned are used. They both say that tangent cones are better than arbitrary limit spaces.
But an equal 4 will have a reflected singularity with only points.
Yeah, only points. So everything is in
S0.
S0. Yeah, so in dimension 4, it's empty except for Sn minus 4.
But in general, we don't have shift by, we have singularity dimension the same like at k minus 3 or something.
It's empty. So
No, in general.
No, well, this is all I've said so far. I'm getting to the next part. Okay. So, if you wanted to prove, according to this theorem, in general, that the singular set is codimension 4, which in the Einstein non-collapse case is conjecturally true, what you should try to prove is that the whole singular set is Sn minus 4. And the way you would prove that is to have an appropriate epsilon regularity theorem. So if it weren't, if something higher, it would mean it would be some tangent cone which split off an even bigger Euclidean factor. And then if you could prove that that was incompatible with your hypotheses by a suitable epsilon regularity theorem, we would be done. And that's what's done. So that's how you get the codimension 4. So without any other assumptions, here, just with Ricci bounded below, the second fact is that in general, singular set is Sn minus 2, which says that if it splits off Rn minus, if a tangent cone splits off Rn minus 1, then it's really Rn. Now, you could believe that because if it splits off Rn minus 1, what could it be if it's not Rn? It would have to be a half space. Now, theoretically, that could occur, but you have to show that it can occur as a limit of things with Ricci bounded below. It certainly is a cone that satisfies that, but you have to show that certain cones don't occur as limits. So with no other assumptions, that half space, I claim, doesn't occur as a limit. You can think why, because it has this kind of internal boundary. You make a ball. The boundary of the half space is on one hand part of its boundary, on the other hand it's the limit of closed things where the boundary is. Instead of points at distance 1, it's a ball of radius 1. So it kind of looks like there's something fishy about it. And just for topological reasons, you can show that half spaces, although they're perfectly good cones that split off Rn minus 1, they don't occur as limits where the lower bound on Ricci tends to 0. So for this reason, non-collapsed Einstein manifolds have singular sets which are closed of codimension 2. Now, if you could eliminate the two-dimensional cone cross Rn minus 2 in general, it's easy to do the three-dimensional cone cross Rn minus 3, and you would wind up with a singular set of n minus 4. This is conjecturally what you can do, but at present, embarrassingly, you can only do it assuming special holonomy and by a kind of case-by-case argument. So of course, a picture to keep in mind that shows that this kind of captures, you can't do any better than this if you just looked at a convex surface with a bunch of conical singular points. Just from Ricci bounded below, they could, in fact, you could have a countable number. They got less and less conical. It would be very flat cones, but you could have a countable number of dense ones if you only had Ricci bounded below. But if you have a two-sided bound, then there's another epsilon regularity theorem, which I don't have the transparency for, which says once they're very weakly, once they're almost flat, then with a two-sided bound on Ricci, the Einstein case, they're really flat. So actually, I forgot, I do have a slide for it. So that's this. The two-sided bound, no other assumptions. If it looks very close to a flat wall, then it's non-singular in the Einstein case. Okay, so then, as indicated, in general, without special holonomy, you prove codimension 2 by eliminating half spaces as cones by just a topological argument, it turns out. And presumably, codimension 4 without this kind of refined discussion that was conjectured by Mike Anderson. Now, as you would expect, in the case of special holonomy tangent cones, the structure should reflect the holonomy group. So, for example, in the complex case, the Euclidean factors which split off are, as you would expect, in some reasonable sense, or they must be complex subspaces. It's very plausible because J of a parallel field is parallel. However, this is not so trivial to prove, it turns out. You have to say that a cone is different from a cylinder, where J of the axis is parallel, all right, but it's not tangent to a line, it's tangent to a circle. So this turns out to be plausible and true, but harder to prove than you might suppose. But in any case, the strata have even codimensions, and so this fact, which is true, explains why there's a gap. Sn minus 5 is equal to Sn minus 6. There's nothing in between. That's a theorem in all special holonomy cases, and that's why you hope to control things off a set of codimension 6. So quickly, just mention the other things that you can prove. So to go, so actually, without assuming this yet, just without assuming anything about an integral bound, just say special holonomy, you can prove that along the top dimensional piece, at every point, there's some tangent cone which looks like Rn minus 4 cross R4 divided by a finite p. That you can prove in the same way that you can prove codimension 4. It turns out they're very closely related. But if you have an L2 bound on the curvature, and this is, as it so happens, even without special holonomy, you can prove that the tangent cone is actually unique almost everywhere along the singular set. In principle, you could take any blown up limit, there might be more than one. In general, there can be more than one, but with this bound, you don't even need special holonomy for this. Along the top piece of the singular set, the tangent cone is actually unique and an orbifold type almost everywhere. As I guess I just mentioned previously, even without the integral bound in the case of special holonomy, you have existence of at least one good tangent cone. And now we're almost at the end. The last thing that I want to state, the whole other discussion, is that not just at the infinitesimal level, but you can say something about the structure of the singular set at a fixed scale. Namely, it's a Lipschitz manifold in the measurable sense. And that implies that it has locally finite bounded subsets, finite n-4 out four-dimensional measure, and it has this measurable Lipschitz structure. Now, we want it to be actually a totally geodesic submanifold, but this is the best we can prove at the moment. It's a kind of comparable state of progress to the case in harmonic maps at minimal surfaces. I don't think there's any example there where you really get a rectifiable singular set, as far as I know. It's probably much nicer. This is what we can do. Now, there is certain contexts where this can be a step on the way to proving that it's much nicer. But although there's, in geometric measure theory, this rectifiability, which I'll remind you of the definition on the last slide, plays a big role in geometric measure theory, and there are various theorems which guarantee that a set is rectifiable. There are various criteria. But you can't use any of them here because they all apply to subsets of the Euclidean space. Whereas kind of a big point in this discussion that's missing is that you don't get any nice natural embedding of the limit space in the Euclidean space. So although it's rectifiable, you have to kind of construct this measurable decomposition into pieces by Lipschitz to